Good afternoon, ladies and gentlemen. Welcome to the next session at the DSF this year. It's going to be my great pleasure to introduce Ebru Cucen from OpenCredo. He's going to be talking about connecting the dots, harnessing the power of graphs and machine learning. Ebru is one of the lead consultants at OpenCredo, and she's passionate about turning data into actionable insights. She believes that graphs hold the key to unearthing novel and interesting answers to some of the most challenging connected data challenges in business. Ebru.
Thank you. Welcome to my talk. Today I'll be talking about the graphs, how we harness them and how machine learning is helping them. I work at OpenCredo as a lead consultant. My background is on software engineering and mathematics, so I try to combine both of them, and graph data science is the perfect place for me. I have published a book on graph machine learning. You can find out outside at our booth. It's free, you can download. And it helps to understand what are the use cases for graph data science, machine learning algorithms that helps daily lives improve every day. I'm aiming to show a couple of graph machine algorithms, how they shaped our life, and I will talk about machine learning, ignoring artificial intelligence, because that's a totally different topic, but from engineering point of view, how we engineered, how we modeled, how we changed the algorithms. Machine learning itself tries to make better predictions. We had lots of data, tsunami of the data, and we had accelerated cards. They all help to speed up the process, and now machine learning is like saturated area. Everything is being done. We can do object detection, you can do sequence audio file processing easily. But I challenge here, it's not done because they can't process graphs. Graphs are not structured data, as we call it unstructured data. And in this talk, I will try to explain what are the challenges it brings and how people are approaching to solve these problems. I forgot on the note, just to clarify, throughout the talk, I will use the left-hand side as the data and right-hand side as the schema. So it will show how the graph actually we are going to build throughout the talk. And I hope it will be intuitive to show how you can model a graph. And my goal is graph is the most native data format because it has built-in semantics, understanding inside it. The second one is it created a new era in the machine learning space, which we think it's saturated, but it's not. And there are so many researches are being done. It's still progressive. It has lots of gaps needs to be filled in. And it's very useful for everyone in the data space. It's useful for the data analysts. It's good for data engineers. And it's good for data scientists to explore this new space. Don't take my word for granted when I say graph is the most native data format. I don't know if you recognize him. He's the CEO of NVIDIA, and they had the conference a couple of weeks back in November. He was the keynote speaker, and this is his slide deck. You can find the scanner on the left-hand side if you want to watch the keynote. It's awesome. It all talks about the data science and how they are helping to accelerate. But it's his words, graph are the most native data format, most natural data structure of the world's data. And for the ones who doesn't know NVIDIA, they are the processors or GPUs, the kind of biggest machine learning chip manufacturers on Earth. So they know better than I do. I believe he's a better reference for me. And one of the arguments he makes is actually similar to what I said, that data structures up until now, we thought it's unstructured. Oh no, it's a weblog, it's audio file, it's an image. It doesn't like the traditional databases. But they have a structure. Audio file is a sequence, one by one, or weblogs. They have the sequences, you can process them. And RNNs, the recurrent neural networks, actually is really good at processing them. And images is 64 by 64. It has a format, it's structured. You can, pixel by pixel, you can calculate what the structure or the prediction will look like. Is it a cat or a dog? And CNNs are really good at the convolutional neural networks. These problems have been solved. But the graph structure is not a structure. It can have millions and billions of nodes. And if you want to represent in a matrix, each one is unique. You don't have a structure of the node itself. You don't know how many users, how many products you will have. So it is out of any format we know, and it hasn't been studied enough. Before I start, I want to learn about you. How many data scientists we have kind of day to day? Okay, almost half. How many data engineers? Okay, are they the same people as well day to day? Good. How about data analysts? Okay, yep, 1/3. Good. And in terms of the data science, NLP specific? Well, good. Object detection? No, one maybe. Who else? Kind of what else are we doing? What is your specialty or kind of problem you are trying to solve? Recommendation engines, maybe? Sorry? Computer vision, yes. Okay. Any else? Specific problems you are trying to solve? Clustering, okay, yeah. That is close to graphs. And has anyone worked with graphs? Was going to my next question. 1, 2, 3, 4. Yeah, that's very good. 5. Let's go back to our basic graph. We can definitely make it more descriptive. So what I added is the Data Science Festival as an event on my schema, and also as a node, and I kind of added some random guests because I didn't know your names. I put some data and other talks like awesome data science and football data analysis. So how does this help? First, to be pedantic, this is a directed graph because the relationship between nodes have an arrow, so we know which way it navigates. A graph can be directed or undirected, and this will be a directed one. And also it's heterogeneous, means I have multiple types of nodes, a guest, a talk, a speaker, they're all different types. We will also have weights in the future kind of coming, because rating, for example, a guest may rate differently a talk, which is based of recommendation engines, actually, how we come up with. This will show the strength of the relationship. Is it a knowledge graph? Kind of, this is a bit tricky question because there's no common agreement on what a knowledge graph is, but there are some common features. They show, one of them is they have a schema, so they should have a structure around it to represent, and they use usually ontologies, like the data glossaries or data dictionaries, so that you can reference and create. The second one is, it is not a knowledge base. You can't infer a knowledge base. It's just the data, fact data, whereas knowledge graph is a reasoning engine that you can go and ask questions and you can get feedback. So kind of there are the two things distinguish on the graph. Also, you don't have to do multiple joins. The relational database versus graph databases comes always a challenge, but with relational databases, you have to do multiple hops to be able to navigate between two users. The structure doesn't allow you, and it's very costly to go to from William to Douglas, whereas on my graph it's easy, or to the third, fourth, kind of multiple hops. When we construct a knowledge graph, it becomes a search engine. More than search engine, it becomes a question and answering machine. This is an example how we can enrich our data. One of the guests was apparently messy, and I went to Wikipedia, and because we all love crawling, I guess kind of one of our data sources, we do love multiple sources. Wikipedia is one of them, and I can crawl his birthday, birthplace, and other information about him, or whoever is in Wikipedia, I can find it and ingest into my database to make it rich enough. There are about 100+ data sources you can ingest. If you are working in a moderate data, there are more than 100 sources you can ingest from the public sources, open data sets, linked data, and other sources. It's just now web is out of our imaginary. So many published data sets are available. But does this help me actually to identify the guests? Which ones are similar? How can I cluster them? Can I create the communities kind of and understand who likes? If I want to sell a product, can I sell? Who am I going to solve this? All this relevant information, important or non-important, isn't they are money related or charity related, can help us. So if you don't know something, if you don't know a question, like you go to Wikipedia, but what we do also, we ask Google, right? If we have a question we don't know, we want to learn more. So let's ask, where is the data science festival? Your expectation is when you ask Google, where is the data science festival, it's going to display the most relevant answers, which made Google Google. The algorithm behind it, who knows, by the way, without me saying yes? What was it? The algorithm behind the search engine. Yes, PageRank. PageRank is actually a centrality algorithm, which is part of graphs. So it's a graph algorithm. It's a centrality. It tries to find the most influential item in the graph. So behind the scenes, there's a graph, and it sorts and finds the top ones if the relevancy are the same. But I'm not going to talk about that, because Google made enough money. Maybe they didn't make enough money, actually, because they realized if you go to Google and click the first, top 2, whatever, because it's so good, the top results are good enough, you click them, you leave the page, Google doesn't earn any more money. It's not good for Google's business. So they had to make you keep on the page. So they had to find what you're after and display it on the page. So they came up with knowledge graph in 2012, and they put on top of the PageRank and search everything. Google became a question and answer engine rather than a search engine. So it does display those results. And now Google can earn more money, which is good or bad. This is another example. If I ask when it's going to happen, because it knows, because it goes to lots of resources. The first one is Wikipedia, easiest one, but also they search the whole web and find answers and displays the results on its page. So how we construct a knowledge graph, it's one of them kind of, if we have Alexa, it's not just Google, Alexa, Google, Slack, and Facebook, they are all doing this. It's a question and answering machine. They crawl the map, they edit their data sets, the mappings, dictionary, and then they semantify it. It means they create their annotations out of this data. And they store in a database, sometimes a MongoDB NoSQL database before the GraphDB, and then eventually they end up in the GraphDB. Then when we ask a question to any of those, they do NLP, synthetic analysis of the question. They do entity mapping, and they try to create a construct that query and execute it. So it finds the relevant subgraphs and answer your question. So this is knowledge graph, the first implementation of graph we talked about is in use for your daily lives if you go to Google next time. The other one I want to talk about is a more fundamental base. It's pathfinding, traditional one. And I thought I can show this with the tube stations because it's the most common use case where you use the one station to the other and navigate through the path. So my assumptions are every guest in my model lives nearby a tube station. To come to CodeNode, which is the host, also is located nearby the tube station, and you have to use a couple of hops. If you are staying at a hotel or you haven't used the tube today, apologies, but that's one of the constraints I had to do. Two things. One of them is what is a walk? If on my graph I visit one node, if I traverse the nodes, it's called a walk. And if I visit a node once, it's a path. So they are a bit tricky. But my question is, what's the shortest path from Victoria, let's say, to Liverpool station, which is kind of my CodeNode's closest place? We did the same thing. We asked Google. So Google is a question answering machine. They did search. They found the Google Maps. And Google Maps is going to answer translate my query into a graph. And actually, in the scenario, the output will be a graph. This is a tree. It's a directed tree because it has a single source node, and it doesn't. Actually, in this scenario, it's not going to be. It shouldn't be cyclic, though. This is not cyclic because it's one way. It doesn't go back. So, with the tube stations, you can by mistake, or you can go from Westminster back to Victoria if you pick the wrong platform. But let's assume everything is correct. So it's directed tree that it's either the family tree or anything you can think is a graph, and this is a graph too. So it does calculate the shortest path from Victoria to Liverpool Street Station. In my graph, I tried to put the different colors for the different lines, and I also put badges to display the times it may take on average. It's from another data source I ingested, so it may not be correct. But the idea is similar to what Google Maps is doing.
Isn't that plain wrong?
Sorry?
It's plain wrong, isn't it? Because it's Victoria to Oxford Circus.
The Washington City is closed. So
Wait,
that's the way you can do this.
No?
No.
This is the trouble of my data set. It's an open source data set I did use, to be fair, but I will blame TFL API. I worked for TFL, by the way. It's a great company. There is no offense. The graphs are inherently in our lives every day. If you are using telephone, mobile phone, all the connectivity, your calls, messages, and everything is done through communication with the providers. Any congestions, disruptions on the network is going to impact you, so it is calculated through the graph algorithms. If you are connected to Wi-Fi or you are using mobile data, internet packets, all the packet routing is done through the graph network as well. If you order anything from online or a store, supply chain management itself is a graph. From the factory where it's produced to the warehouse where it's delivered, when it's delivered, via which route or which van truck it's been delivered, to which stores it's going to be displayed, and then which kind of home addresses it's going to be delivered to. So it's the whole network is also a graph, and everything being calculated for the fastest route or the shortest path is going to be done by the graph algorithms behind the scenes. You may be doing day-to-day, that's also exception, but as a consumer, we all are part of graphs around us. Also, our brain is, I said it's my as well, it's not exclusive, but our brains are structured as graphs as well. Neurons and axons, they are all communicating and passing the information from one to the other. Is also how it works. And then having said that, lots of people I will hear, hey, brains was inspired neural networks. That's how the neural networks started. They were kind of similar structures. They pass the forward propagation where we have the data to the next one, to the next one. Kind of. Yes, because neural nets are also networks. And having said that, I can just leave this talk here because machine learning, neural nets are the crown jewels of machine learning. And graphs helping neural nets, I just conclude kind of my talk. It serves the topic, and I can just finish here, but I'm not. We'll talk about a couple of things, the challenges it brings. Before we go to neural networks, I just want to mention random walks because it's relevant to what we are going to do, and it lies as the base structure for most of the neural network calculations. Random walk is a drunk person walking, so it doesn't have any probability. It can go to any adjacent nodes with equal probability. So if it doesn't have a bias, it doesn't know which node it's going to next, which means it has the maximum uncertainty, and in statistics it's called local entropy. It used to measure the structure of the graph, which is, if you want to calculate World Wide Web, we would go and do random walks, so we can go to the unknown nodes easily. Without any bias, we can travel further, and this is how actually World Wide Web is calculated. We can also do sampling, which is important for the machine learning algorithms. It can either sample the subsets that we want to work on, or it can sample the negative scenarios where we want to say, this is not the case we want, this is kind of the negative sample we want to have. Back to neural networks, and I will talk about graph neural networks specifically. They are inspired by neural networks, and they behave similarly. They have the same flow. And they have similar challenges in terms of embeddings, samplings, calculating the loss function, but in a different perspective. This is a standard graph neural networks. It was published one of the articles. It's not my drawing. But what we do is first we find the graph structure. We specify the type, how it's going to be scaled. And then we design the loss function as standard kind of what is my algorithm will look like. And the last part is building the computational module. And that computational module is actually either finding those samplings, running the convolutional or recurrent operators, and then finding that pooling operator max min that we do. And then the output will be either node embedding, edge embedding, or graph embedding. So my awesome drawing is here. This is standard neural network. If you didn't recognize, apologies for it. I have input layer, 2 features, x1 and x2. And I calculate kind of the matrix is 2 by 1. I want to calculate my set with the weights, so I just multiply with the matrix multiplication. And this is the standard scenario, right? It's the simplest form. I can have my sets calculated, and I do forward propagation, find them, calculate the output loss function, and do the back propagation to improve my model. There was also activation function after that, which could be ReLU sigmoid or tanh. Now, the challenge for the graph is I don't have nodes. It's not x1, x2. I don't have scalar values. It's the feature I'm talking this time is a graph. It has a bigger matrix. It's not one cell, one scalar value. I have a matrix n by m. And now I have to think about all the adjacent matrices, kind of the sparse data I have. I need to think about how I'm going to create the subsamples, how I'm going to activate, kind of apply the activate function, and how am I going to calculate the loss function. It's becoming more sparse and big problem. So if we think about the loss function, how we calculate, the standard is we were taking the x, kind of whatever we want to apply. In this time, if we are talking about edge as the node, I can just do edge level loss function and calculate that value for that. If I want to do edge level, which is the second case, it's link prediction. Then I need to think about what that link is connected to. So I need to put the calculations for the previous and the after nodes connected. And also, I can do the graph level loss function to calculate if this, it's unusually used for chemical compounds, if a drug is causing a disease for that specific chemical compound, so they compare the compounds. And I can design my loss function. OK, my expected graph looks like, and this is what the output. So what's the difference between those two graphs? One example about GCN, which is the graph convolution network, which is inspired by CNN, the convolutional neural networks. Has anyone heard of Zachari's Karate Club? Yeah. It's a researcher, kind of. So he was studying a karate club. And at the time, he was documenting the interactions between the members of the group to find out how they are clustered, kind of how they are creating subgroups within that one. And they had 0 notified as the Mr. who is the instructor. And the other one is number 33, which is going to be relevant because they are the central ones, if visible. It's called John A. And during his study, actually, there was a conflict. And the group was split into two. Some people, because John A argued with Mr. Hughes, so they split into twos. And some people continued with the original instructor. The other people either left or they formed a new group. So he managed to actually, and this will be number 30, by one mistake, he managed to predict this beforehand during his study. So this is why kind of community detection is quite important, and his study opened up new era for the other further investigations and implementations. He didn't use GCN, he used basic clustering algorithms, but what I'm going to show is if we take this data and do some modular algorithms, clustering is one of them, and greedy clustering we can implement, we can find out 4 modules, so we can have 4 classes of the same data set on the right-hand side. And even during my clustering, actually, I had the number, oh no, number 9. Will be separate, kind of different colors, but I'll come to that. So this is the greedy clustering. We made the 4 classes, and there are so many. I said the machine learning for the data science people doing lots of work in academia. Also, there are so many libraries, Python libraries and other libraries being written right now. Torch geometric is one of them, PyTorch geometric. DGL, Deep Graph Library, is another one. They are like the scikit-learn versions of the graph world, so it's increasing. We have so many new data sets and libraries that helps to write the queries easier. And I use the Torch geometric GCN com class, and I ran this for 400 times. And it's 94% kind of accuracy that does find out what is those 2 groups are split into. So it's 94% accuracy is not too bad, and I think it does serve with the clustering how you want subgroups and compute the GCN. Last one I want to mention is recommendation engines, because I said that, okay, we have some guests back to our original graph, and they rate some talks. Again, some assumptions, if I'm kind of to do this, it may not make sense. Data Science Festival can use this if this talk was recorded, and they were going to cross-sell this talk to other users who haven't been, or who were not part of it, like Udemy or Coursera or other places. They do record courses or presentations and cross-sell. That's part of the recommendation, so a guest can rate it, and depending on that rating, the website or the company can do recommendations for other talks. I mean, my bipartite graph looks like this. I have the other users. But rather than kind of going this one, there's one specific article, PinSage article. Has anyone heard of it? PinSage? It's actually one of the latest, best state-of-art algorithms for recommendation engines. It's written by Pinterest. And if you are using Pinterest, that's how they recommend new pins to you. In that article, actually, what they did, they unified the pins and the boards, in a sense, collectively. And out of this, they created some batches, mini batches. To be able to do sampling, those mini batch samples, they use random walk. So they picked a node and they tried to find the unbiased neighborhood of that. And it was 50, so they picked the 50 neighborhoods. And they take it as the first sample, second sample, third sample. For each iteration, they use that random walk to create those samples. But you also need a negative sample, right? You also want to say, if this is a flower I'm going to show, I don't want to see a clock appearing, or kind of comparison between those two. People wouldn't be interested in a clock if they want to see a flower. For negative sampling, they use personalized PageRank. Because if a flower has no relevance or connection to a clock, it should be further away in the graph, because the graph can represent the strength of the connectedness with the number of hops. If it's too far away, it means they are not connected, because it has semantic inside it already built in. So they said, OK, I can pick the personalized PageRank algorithm. I will collect back to those 1,000 to 2,000, whatever the range, kind of further down. And I will pick those ones as negative samples. So by doing nothing, kind of without going to extra, they managed to pick the samples, they managed to pick the negative samples. And then they said, OK, we want to calculate the loss function, kind of how we are doing that. They decided to use the concentration for the pooling without going to the boring stuff. And they did 2 billion of images. I think it was under 24 hours of calculation. So they managed to recommend and run the algorithm to display. And also they did some nice things about the CPU and GPU, how they run the parallelize and mini batches. So that was something I want to mention. Recommendations engines are great. Also, there are so many good articles published in the academia, which actually I want to show that by numbers proof. This is from dimensions.ai. If you are interested in kind of, that's a website, tells how many articles, how many data sets, how many publications have been done. And I search for graph and network. You can search for something else, but that's my mental navigation. For graph and networks, over the next decade, there were 98,000 publications, and that's from 5,000 growing exponentially. Similar to the graph neural networks, actually it's a bit more exponential in a sense that there are 15,000 publications. It is very becoming trendy, and kind of I'm sure there will be more innovations happening soon. And it's an end-to-end process. I just show actually that with the data analyst can write a native query from one station to the other. I can have the data engineers with unbounded extension, because you can add more data into it. If, like the Wikipedia example, enriching the data set is so easy, creating that knowledge graph, and I don't have to add another column like the relational database. If you add a new column, you have to think about what are the existing values have to be, what I'm going to extend it. It's such an easy job to merge data, append data, and create reasoning with the graph representations for the data scientists, because now we have more data, we can semantically understand and reason about it. That is almost actually me done. Back to what I said, I believe graph is the most native data format with built-in semantics. Graph open anywhere in the machine learning, none of us can ignore. And graph is very useful for all type of roles. Either you are a data analyst, or data engineer, or data scientist. It will be helpful somehow. Thank you very much.
Thanks, Ebru. We've got time for a few questions before coffee. So has anybody got anything they'd like to ask?
Or I can take at the booth as well. We will be around the corner.
So back in the slide where you had the graph and then the graph neural network conversion, the graph conversion, the GCN on the
Yeah.
How is the convolution done on the graph? Because how you do convolution on pictures, because you have this graph between a node, a pixel and its neighbors, and you can do that convolution on that flat space if you wish. But as you said, the graph, it goes like, you don't know how many neighbors it has, for example.
Yes, it's represented as the adjacency matrix.
Okay.
So you turn into like a tensor. So you usually turn into a tensor vector.
Yeah.
For the graph, you turn into a matrix.
The adjacency matrix. Okay.
Yeah. The relationships between them is the adjacency matrix, and they form, and you can apply that for each layer, kind of, and the output will be a matrix as well. So it's very easy to. It's just bigger size of. Thank you. Any more questions?
Another one here.
Okay.
What did you use to plot your nice graphs? They look pretty good.
Okay, it's called Hume. Actually, we are partners with Hume. I'm not trying to sell, I didn't say. It's Hume GraphAware is the company. Hume is the product. Hume. We have stickers as well at our booths if you are interested. Thank you.
Great. Let's thank Ebru again.